I want to derive, as the last part of this particular series, an alternate formula for curvature. It's a great example of vector algebra and geometry in action. You'll see in a lot of places, in particular in our textbook, this formula for kappa. It's the velocity crossed with the acceleration divided by the speed cubed. And it's rather unexpected. The cross product, what is that doing there? We haven't seen that in a little while. Why speed cubed on the bottom? We have some reasons to believe that we need to divide by the speed, but why speed cubed? And I want to go through basically just elaborating our book's derivation of this. Nothing particularly different, but it's not incredibly well explained or maybe motivated. It's a little bit too terse, as it usually is in books. So first of all, let's just have some abbreviations. So r prime, of course, is the velocity. That's just v. R double prime is acceleration, that's a, and then magnitude of the velocity. I don't usually do this, because our book doesn't usually do this, but the physics convention is when you have a vector quantity, if you just leave off the arrow, you mean the magnitude of that thing. One good reason why you should always put arrows on the vector if you mean the vector. So I don't usually do that, but we'll do that here. It's very, very nice to do that here. Okay, so let's look at this just a little bit to make sure that it maybe has some validity. First of all, it's talking about the acceleration, and that actually is very, very natural. Because if you think about, if you had zero acceleration, then your velocity is constant, you're going in a straight line. And so then the curvature should be zero. So there really should be a formula involving the acceleration for the curvature. And then the question is, why this formula? So it does make sense that the acceleration is involved. Then the cross product, we're going to discover the cross product is there really to relate the fact that we need to know not just how big the acceleration is, but in what direction is it. And in particular, if r double prime is parallel to r prime, if the acceleration is parallel to the velocity, what's going to happen? Okay, you're going along, and my acceleration, here's my velocity vector, and my acceleration is parallel to that. It's just going to make me go faster. Or if it's anti-parallel, if it's a negative scalar multiple, then it's just going to make me go slower. It's when the acceleration is not in the same direction as the velocity that's going to make me turn, and that's going to cause curvature. And this, the cross product, vanishes exactly when the two vectors are collinear. And so that actually makes a lot of sense. We're just not sure why it would be true or how to derive it. The last thing is, why have velocity cubed or speed cubed on the bottom? That's easy to do from unit considerations. Let's just rewrite this. This is the magnitude of v cross a over speed cubed. Okay, and this is how a physicist would verify that there's really something at work here that makes sense. This would be like meters per second. This would be meters per second squared on the top, divided by meters per second all cubed. And what do we get? We have one extra meter on the bottom, but then we get per seconds cubed, and we just get 1 over distance. Remember that formula, the kappa is 1 over the radius of curvature. It has units of inverse length, and so the units are correct. So it's not totally implausible that this would happen. Okay, so let's just erase everything. Let's start with our actual formula, our known formula for curvature. This is something we do know is true. It's the derivative of the unit tangent vector, then take the magnitude of that, and then divide by the speed. Okay, and I want to get from here to the formula that with the cross product. So the key really is what makes curvature calculations hard, and what makes this the key to this thing as well, this derivation, is the relationship between the unit tangent vector and the velocity. The velocity is easy to calculate. It's just the derivative position. Unit tangent vector, suddenly you divide by the speed, you get square roots, blah, blah, blah. It's nasty. Okay, so I just want to illustrate. This is one way to express the relationship between velocity, which includes the speed information we kind of like to kill, and the unit tangent vector, which is with that velocity, that speed information killed. Okay, and it's just, I'm just rewriting the fact that the unit tangent vector is just the velocity divided by the speed in a way that talks about multiplication instead of division, which is always simpler. Okay. Now, what was the other observation? The observation was that it totally makes sense the acceleration should come in here, And so we should actually calculate the acceleration. Okay, that's just the derivative of this, and this is not so bad. This is something that algebraically is not bad. We've got a product rule, and it's easy to verify that when you have a scalar function times a vector, and you take the derivative of the product, you just get what you'd expect for the product rule. This is one of our theorems. Okay, notice what we got here. Ooh, this is part of our definition of kappa. Okay, and then there's this other stuff here. Okay, and notice what's going on. This has to do with the change in speed, the rate of change in speed. This is the derivative of the speed. Are you speeding up or slowing down? And then this should have something to do with the turning. And we're going to actually go further with this in another video where we actually sort of decompose the acceleration into these two parts and talk about it a little bit more. What we're doing here is really very similar to that. Okay, but the really nice thing is that this is algebra, but it's also secretly really nice geometry. Okay, because t had a nice geometrical property that it was a unit vector. Okay, so let's draw up the curve again here. So here we've got t, and what we can discover here, here's a little claim. This is something we do as a book problem in our class. One of the things about t is that it's a unit vector. It's always got t dot t equal to 1. And if you take the derivative of both sides of that equation, use a similar product rule, but the product rule for the dot product, and divide by 2, what you get is that t and t prime have dot product 0, or t is orthogonal to t prime. Aha! So t prime is like in this direction, exactly orthogonal to this guy. And that means that this kind of decomposition of A is very nice geometrically. This is exactly how you want to decompose a vector into two orthogonal pieces. So we've got A, maybe it's going off, maybe like this, okay? And we've decomposed it into two orthogonal pieces. And that's as I said, we're gonna keep going with that idea in another video. And so this part here is the v prime, oops, that's the speed prime t. And then this guy here, the projection onto here, is the vt prime. Okay, so it's all about projections. And now we want to think about, okay, we're really interested then in this part of it, because we want to just isolate the t prime to be able to stick into here. So what's the best way? The t is kind of the initial data that's easy to deal with, because that's related to v. That's something we can get easily by differentiating the position function. So if we wanted to get this part, we would project onto t, and we know about projections, and that's about dot products. Unfortunately, we actually are caring more right now about projecting the acceleration vector onto t prime, which is the complicated part of the story. So instead of the dot product, what we're going to do is we're going to use the cross product. Okay? What we want to do is we want to do something to this combination that kills this guy and leaves this guy, relatively untouched, or at least doesn't kill it. And crossing with t cross a, that would do it, because t cross t is 0. Okay, now, really, even better than t, though, would be crossing with the velocity vector. They're parallel to each other, and so it's going to be better to cross with v, because we really want to get a formula that just involves just derivatives of the original position function r. R prime, r double prime, that's it. Okay, so we're not going to quite do that. We're going to take v cross a. Okay, so what is that? It's the vector v, okay, cross this guy, v prime t plus v t prime, okay, and I'm going to remember that this v is v times t. That's the geometrical operation of taking a vector and always thinking magnitude and direction. Okay, that's never a bad idea when you're trying to think geometrically. Okay, so it's really about these very basic cool geometric ideas with vectors, of projecting things onto other vectors or onto their perpendicular vector, magnitude and direction decomposition. And there's always ways to do it algebraically with dots and crosses and scalar multiples. Okay, so now what's going to happen? Okay, the t cross t is going to die. That's going to go away. I've got v times v, so that's a v squared. Ooh, we're getting powers of v. Oh, that's pretty good, because we want to get a v cubed eventually somewhere. And then we've got t cross t prime. Okay, and you might think this is where we would have to stop and get stuck, because cross products are not super simple. They're the most complicated of our vector geometry operations, or vector algebra operations. But remember what we really care about. We really just care about magnitudes here. We're not really trying to get a vector out of this. We'd love to have something that just isolates the magnitude of t prime. So let's just take the magnitude of both sides and see what happens. So I'll have to go back up here. Okay. Let's take the magnitude of v cross A. Okay, the magnitude of a scalar times vector is just the absolute value of that scalar, but since it's squared already, we don't need to put it in absolute value signs, excuse me. And then here's the last place where we use the geometry. It's really crucial. T and t prime are orthogonal to each other. The magnitude of a cross product, when those vectors are known to be orthogonal, is super simple. It's just the product of the two magnitudes. Okay, so that's cool. And now we're getting the magnitude of t prime in an equation where the other side just talks about velocity and acceleration. We're almost home free. What is this guy? Think about that for a second. Pause the video. It's 1. It's a unit vector. So that goes away. Okay. So again, it's this wonderful interplay of algebra. We're doing like distributive law and algebraic stuff. But every time we get a new algebraic fact, we also combine it with a geometric fact. Like, hey, that's a unit vector. Okay. So we've got a new formula for t prime. And that's basically all we need, because then we're just going to divide by v. We're saying that t prime is the magnitude of v cross A divided by v squared. Okay. And what did we want? Kappa is, of course, the magnitude of t prime. The reason, remember the reason we had to divide by the v. Whenever I'm taking these primes, they're all with respect to the t variable, which is great. That's the easy thing to do. It's the given parameter, but it's not the geometric parameter. We figured out there was an easy fix for that. Just divide by the speed, and we got that out of the chain rule. Okay. And so that's just going to be this. Now it's going to be divided by v cubed. And we're done. Okay. Remember the physicist's proof. The physicist's proof was, you show me this formula, and I verify it's going to give me 0 when A and V are in the same direction, so that's just speeding up, slowing down, no turning. It gets in the right units. It's pretty much got to be true. Okay. But we've now determined this really is true from a more mathematically careful perspective. So there's that alternate formula for kappa, and that's a really nice formula because it doesn't require anything but just calculating the velocity and acceleration, which are usually easy, the speed, which is easy, and then the only thing is the magnitude of a cross product. There's a little bit of algebra there, but it's actually a very, very nice formula.